Fukumoto. And this paper also got a Best Paper Honorable Mention, so congratulations.
Oh, thank you. Hello, thank you very much. Thank you for introduction. Hello, I'm Masa Ogata from Keio University. This work is done as an internship in Microsoft Research Asia and supervised by Masaaki Fukumoto. Today, we propose a new paper media using magnetic flux. We named it FluxPaper. Let's start from video. FluxPaper is new material for paper interaction. FluxPaper has very thin magnetic layer behind the paper, and it realizes various kinds of interactive applications. It's a card stacking, and we can select only one card. Okay. And I'm giving my presentation with this outline. Our first question was how to create a fast and powerful active paper media. Then our solution was magnet. We tried to combine the magnet and paper. Then the magnet plus paper equals FluxPaper. FluxPaper has a very ultra-thin magnetic layer with 0.1 millimeter. By using resin, the layer is durable and flexible. It realizes powerful actuation without any contact, only using magnetic power, even if without electromagnet. Magnetic layer has magnetic layer has a high flux density, and this pattern can be programmed. You may know about the rubber magnet or magnetic printing paper. Rubber magnet is thick and weak and just can be attached to the iron plate. On the other hand, FluxPaper is very thin and strong and can be operated with various actions. But is it possible to make very thin magnetic layer? Yes, we could. So this is a process to produce a magnetic layer in a laboratory. This is not the final answer, but we can show how to make without using expensive or dangerous machines. First, we got bonded neodymium magnet powder, and we mixed it with epoxy resin. On the foundation, we put the paper and the mixed powder. By leveling off, the magnetic layer became 0.1 millimeter. And after hardening of the epoxy resin, we reshaped this layer and pasted it on the paper. Next, make this layer as a magnet. Usually, magnetization requires high voltage or high current, but we made and used non-electric handy magnetizer. This magnetizer condenses magnetic flux into a spot. So the red part has a very high flux density. So it can magnetize the magnetic layer on the paper. Finally, we could make this thin and powerful magnetic layer with this process. The next point is how to make a pattern or shape of magnetic layer on the paper. FluxPaper had the same characteristic to the magnet. Then, by using the connection between the magnets, we imagine these three types of dimensions can be designed. And This is the final design can be realized by FluxPaper. There's two types of actuation mechanism. The first one is self-alignment. The self-alignment means FluxPaper attracts each other and makes a structure. It works even if there's no external magnet or magnetic field. The second one is computer actuated. That means the paper can be moved or shaped by the electromagnet controlled by the computer. We will show you some relation works. There's some example to be sticked to the board. The left side, magnetic, is a plastic paper to generate electrostatic. And right side, luggage, is a special board to generate electrostatic. So it sticks to the board. But both of them are both of them is not dynamic, just sticking on the board. There's some animating paper. The left one is the idea to move a paper with using the shape memory alloys. But it's dynamic actuation, but it requires the wire on the paper, and also it must be connected to the wire. The center one is wireless and using the heat by laser, but it's a little bit dangerous if it's out of the box. The right side, Pop-Up-E, used heat shrinkable tube and microwave, but it only moves in the microwave oven. So to compare with them, FluxPaper is contactless and fast, and also has self-actuation capability. To find an optimal design of FluxPaper, we did simulation on the software. We used this design to place circle layers continuously. The gray and orange pattern is all magnetic layer, and the thickness is 0.1 millimeter. The main parameter we used, D, is the diameter, and G is the gap between the circles. This is a result of the value of the flux density from the magnetic layer. The red circle shows the highest value. So this is the optimal design, optimal condition of FluxPaper. To verify the result of simulation, we also conducted experiment to make an ideal model of magnetic layer and measured an attraction force. Using this machine, we made a test piece of FluxPaper and measured attraction force using these scales. Then this is a result, and let's compare with the simulation result. Though this is a preliminary result, but the plot seems to be approximate simulation. Now we are going to finish the experiment soon. Okay, let's go to the applications. There's 4 types of applications. The first one is self-alignment and programmed edge. There is each 1D, 2D, and 3D structures. This is a paper for stacking to gather the document into one place. So if you use FluxPaper, you won't be annoyed from the scattered papers on the desktop. No longer. So next one is to make a great design to design of pieces of FluxPaper. So this piece connects each other strongly, so user can grab and move it. The third one is pre-coded magnetic layer can be very designed. By properly designing magnetic patterns, only valid edge can be connected. So if we connect 1 and 1, it can be connected. But 1 and 5 doesn't connect. So this structure can guide the paper crafting like this. Next one. Automated whiteboard is one of the impressive applications of FluxPaper. By using moving table behind the board, electromagnet attracts and moves the paper, FluxPaper. So, why the paper can be moved on the board? Here's a secret. There are 8 magnetic pieces on the back side of FluxPaper, and only 2 top spot has self-adhesive capability. When attaching all spots by the electromagnet, the paper still sticks after dissolve external magnetic field. When moving the paper, top 2 spots are repelled, but other 6 spots are attracted. So it can be moved on the board. And finally, when all spots are repelled, the paper falls. Electromagnet can selectively attract and repel. So this function enhances the characteristic of paper capability much more. These actions are used for notification or making tactile vibration or make a sound to emphasize the item was done or finished to the user. Third one, we can pick up targeted cards from the selected stacked card deck without any type of scan. This image describes the mechanism of electromagnet and magnetic layer on the paper. There's 16 electromagnets and using 2 points for each card. So we could handle 8 cards now. Last application shows self-construction. Using electromagnet, the programmed magnetic layer repels and attracts to construct the object. This is a flow of construction and the design of the paper. And finally, I'd like to show you our goal. This is an image of the printer to implement special printer containing both color and magnetic ink inside. And the magnetizer works when the paper is output. And this is one of the vision of user fabrication in the future. Conclusion. We reinvented paper medium with magnetic actuation and also produced thinnest neodymium magnetic layer on the paper. And we simulated and experimented design patterns. And finally, we developed self-alignment and computer-actuated applications. Thank you for listening, and we'd like to listen to your questions. Thank you.
Hi, Hiroshi from MIT Media Lab. I really like your challenge to augment the paper, but usually paper reminds us as a designer for drawing, sketching, folding, earmarking. And so do you have any idea to use this technique not just actuating or self-assembly or moving by itself, but also capturing the idea or thoughts to the fundamental kind of paperness?
Excuse me, paperless.
Paperness.
Paperless.
The fundamental value of the paper for most of us is capturing the ideas, sketching. So I think there's so many research about the pen-based sketching.
Sketching?
Yep. Yeah. Sketching,
Drawing.
Because,
I never think about that. I'm sorry.
Yeah, maybe for next time. Yeah.
But, okay.
Thank you.
But I think using the same way, we can draw something by using the ball or some object on the paper, right?
Yeah, I think so. Using a special pen,
Yes.
dynamically customize the
Yes,
pattern. I can imagine a lot of things can happen.
Okay.
for-
Let's do that together.
Okay, next time conference. Thank you.
Thank you very much.
Hi, really great work and really beautiful. I really like the part that paper is so thin and so flexible, and then you can actuate it. But the interesting thing is the contrast that, especially when you show your post note, that you have a very thin material that you can actuate, but in order to actuate it, you have a big chunk of actuators behind it. So how do you think in the future that you can also make the actuator invisible, but also design a transformable structure in the paper as well?
Yes.
Does it make sense?
So,
Okay. This is just one idea. By making very micro coils for microfabrication and embedding in the LCD or EL display, we can make the very highly matrixed the coils. It's the similar size of pixels. We can control the magnets without using these bulky the conventional coils. It's just an idea.
Yeah, thanks. So the reason I ask is because there's been also a related work in self-assembly that basically just designing the magnet's position and then the pole so that even if you just give a random energy to shake it, they will arrange and then assemble in the shape that you designed. So, but thanks for your answer.
Ronghao Liang from National China University. I appreciate for your work. I think you provide a brand new type of magnet that can be very useful. And my question is that you showed a lot of potential example on actuation, such as shape assembling, but magnetization of the magnet should be carefully aligned with the actuator, right? Yeah.
magnetizing.
Yeah. The magnetization of the magnet should be carefully aligned with the actuator. Otherwise, the result can probably not what you want.
That's right.
Yeah. So, how will you improve this challenge?
So, it doesn't be the problem because the head of the printer should be the precise. So.
Okay, so in the future devices...
For the future devices, the current printer already have over 400 dpi, the resolution.
Yes.
And if we embedded the special magnetized head combined with a printer, we may have a very precise resolution of magnetizer.
Okay. I see. Thanks for the answer.
Thank you.
I don't know if I'm repeating the first gentleman's question. Vidya Sarangapani, Newcastle University Culture Lab. Futuristic or a future work, could you look at magnetic ink on pens and sketch pens so it could be written on paper and stuck? Is that something that
you mean magnetic ink?
Yes.
Yes.
So you don't have to, like on printers. So is that something that you're thinking of instead of magnetic ink on printers, it's directly on pens and...
Yes.
Yes,
Yes, the image that we showed is one of the answer, I think.
Good. So I think we saw some brilliant talks today. Many thanks.